Have you ever stopped to think about how incredible our brains are? How can a tiny electrical pulse, a little zap inside a single cell, create something as rich and complex as the feeling of joy or the sting of a paper cut? It really does feel like magic, right? Well, today, we're going to pull back that curtain.
So yeah, that's the big question, isn't it? How on earth does our nervous system turn simple electricity into the entire, complex library of human experience? The whole story starts with the brain's fundamental building block, the star of our show, the neuron.
All right, to get started, I want you to stop thinking of a neuron as just some cell. Instead, picture it like a tiny biological battery. It's full of salty fluids, and even when it's just sitting there doing nothing, it's holding a small but absolutely crucial electrical charge. It's just waiting for the right moment to act.
This baseline charge has a name. It's called the resting potential, and it usually clocks in at around negative 60 millivolts. Now, you might ask, why is it negative? Well, it's all about a careful imbalance of charged particles, or ions. To put it simply, there's a whole bunch of positively charged potassium inside the cell and even more positively charged sodium hanging out outside the cell.
And the real secret sauce to that negative charge is the neuron's outer wall, its membrane. It's covered in these tiny little doors called ion channels. And here's the key. At rest, the doors for potassium are about 100 times leakier than the doors for sodium. So what happens? Positive potassium ions are constantly leaking out, and as that positive charge leaves, the inside of the cell becomes more and more negative. Pretty clever design.
So, our little neuron battery is all charged up, sitting there at its negative resting state, just waiting. But what happens when an incoming signal comes along and disturbs that delicate balance? Okay, this is where things get really exciting.
An incoming signal, maybe a little nudge from a neighboring neuron, causes the voltage inside to become a little less negative. So instead of negative 60 millivolts, it might tick up to negative 55 or maybe negative 50. This process is called depolarization, and it's the very first step on the path to that neuron firing off its own message. But here's the thing. Not every little nudge will do the trick. That depolarization has to be strong enough to reach a critical trigger point, a real point of no return. We call this the threshold, and it's usually right around negative 45 millivolts. If the signal is too weak, it's a false alarm and everything just settles back down. But if it crosses that line, everything changes in an instant.
Because the second that voltage crosses the threshold, the neuron goes from waiting quietly to, well, screaming a signal. It unleashes this massive, dramatic, unstoppable electrical spike, and this is the famous action potential. It's the all-or-nothing event that is literally the language of our entire nervous system.
Just look at that iconic shape. You've got a super sharp rise, a quick peak, and then a rapid fall, and the whole show is over in about 1/1000th of a second. Every single thought you have, every feeling, every movement, it's all built from billions and billions of these tiny spikes. So, what actually creates this dramatic shape? Okay, let's look at that steep rise. The moment we hit that negative 45 millivolt threshold, bam! A whole different set of doors. The voltage-gated sodium channels fly open. And since there's all that sodium just waiting outside, and the inside of the cell is negative, a massive flood of positive sodium ions rushes in. That's what causes the neuron's voltage to just skyrocket. But of course, what goes up must come down. The neuron needs to reset, and fast. So right as the voltage hits its peak, another set of doors, the voltage-gated potassium channels, finally swing open. They're a little slower to react. Now, with these doors open, all that positive potassium that was inside the cell rushes out, bringing the voltage crashing right back down. So here they are, our two main players. The sodium channels are the super fast gas pedal, kicking the whole thing off. And the potassium channels are the slower, more deliberate brakes that bring the signal to a clean end. It's this perfectly timed dance between the two that creates that iconic spike shape we see. Now you might be wondering, why doesn't the neuron just keep firing like a broken disco light? Great question. It's because after every single spike, the neuron takes a mandatory break. It's a forced timeout, no exceptions allowed. This happens because of a very clever trick called inactivation. It's not just that the sodium channels close. For a brief moment after they shut, they enter a special state where they are physically unable to open again, no matter how strong the incoming signal is. A fantastic way to visualize this is something called the ball and chain model. Imagine when the channel opens, there's a little protein ball attached by a flexible chain. Almost immediately, that ball swings up and physically plugs the opening from the inside. So even though the main gate is still open, the channel is blocked. It's plugged shut.
This difference is so important. A closed channel is like an unlocked door. It's ready to open as soon as it gets the right signal. But an inactivated channel, that's like a door that's been bolted shut from the inside. It doesn't matter what you do, that door is not opening again until that bolt is removed.
So why go to all this trouble? Well, this brief locked state is absolutely essential. For one, it makes sure the action potential keeps moving forward in one direction, preventing it from echoing backward. And two, it puts a natural speed limit on how fast a neuron can fire, which stops the brain from descending into chaotic runaway signaling. Okay, so we've seen how a single spike is born. But this brings us right back to our original question. If every single spike is an identical all-or-nothing event, how in the world do we feel things with different levels of intensity?
I mean, really think about that for a second. A light pat on your arm and a sharp pinch both send action potentials to your brain. Those individual electrical spikes are the exact same size. So how does your brain know the difference between ouch, that hurts, and oh, that's a nice pat?
Well, the brain has two brilliant solutions. First up is frequency coding. Think of it like a machine gun. A light pat might cause a neuron to fire a few times a second. Pop, pop, pop. But a hard pinch makes that same neuron fire like crazy. Pop, 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 pop. The brain reads a higher frequency as a more intense feeling. The second trick is population coding, basically strength in numbers. A light touch might only activate a handful of neurons, but a stronger stimulus recruits a whole army of them to fire all at once. More neurons firing means a stronger sensation. Simple, but so effective. And all of this leaves us with a final, truly mind-bending thought. The color red, the sound of a guitar, the feeling of warmth. None of these things actually exist out there in the world. They are all constructed inside your brain from the exact same raw material. Simple, identical, all-or-nothing electrical spikes. They're just firing in different patterns, at different speeds, and in different locations. What we call reality is simply our brain's best interpretation of these silent electrochemical storms. Something to think about, isn't it?